All right, what's going on, you guys? Another LeetCode video today. This problem is called word search 2. So we're given an n by n board of characters and then a list of strings, and they want us to return all of those strings that appear on the board. So each word must be constructed from letters of sequentially adjacent cells. So basically, the words, each letter in a word on the board, for it to count, the cells have to be adjacent either horizontally or vertically, just not diagonally. And they can be in any order. It doesn't necessarily have to be all in the same row or column or even left to right. We can see that eat and oath both appear on the board. Eat is backwards, and then oath doesn't, it's not even all in the same row here. We have the O and the A on the 0th row, and then the T and the H, are arranged in a column. So basically, we're going to be doing a depth first search for our algorithm on the board, since the words can appear in any order like this, or any orientation. And we're also going to be using a prefix tree for quick access of those words, quicker access. So let's take a look at the whiteboarding. So on the right here, so if we were given the two words cat and ox, and then this board, this is what our prefix tree would look like. The first thing we have to do is create a prefix tree and then insert those words in there. So we've already done that here. So now we just need to do a depth first search on this board, basically to see if these words appear in here. So what we would do is we're going to do a depth first search on every single cell. So we're going to seed the recursion on every single cell. So we would start with this top left cell here, and then we would check our prefix tree and see if the C, the node for C, is not null, and we can see that it is not null here. So we can keep searching. So we're going to start building this word here from our depth first search. So we have a C. We saw that's in the tree, so that's good. We're going to call our depth first search by incrementing I first. So we're going to try to go this way. We're going to look in the prefix tree to see if that's there, and it is. So we would have gone this way and then this way down the prefix tree. Okay, and then we're going to keep doing our depth first search by incrementing I in the next recursive call. So then we'd have this T, and we'd add that to this string, and we see that it's in the prefix tree, so we can keep going. And then we see that this blue line indicates that this letter is the end of a word. So we would add this string we just created to our result vector, and then we basically we'd be done at this point with the depth first search. And we would remove cat from our prefix tree kind of lazily. It's a little bit sophisticated to remove a word from a prefix tree, and this solution requires a lot of code, so we're simply just going to get rid of this blue line here to kind of remove that from the tree, so we're not searching for the same string again. So we'd be done with this at this point, and now we need to keep doing our depth first search. So we need to go to the next tile. So we'd basically be doing a depth first search from here now, and same thing. So we can see the O exists in the prefix tree. So we're gonna start building a string starting with O. We're gonna do a depth first search incrementing I first. So we go down to this X, and then we see that's also in the prefix tree. So we're going to add that to our string, and then we can see that this is also the end of a word. So we're going to go ahead and add that to our result vector here. And this would be the output. So pretty straightforward example. We didn't have to do too much work here in our depth first search to actually find these words. Kind of did that on purpose, so this would go by quick. But in terms of the time and space complexity, the time complexity of this entire algorithm is going to be, well, we've got to first insert the words into our prefix tree. So that is going to be, if we said that there are m total characters in all of our words, we could just say that this is going to take m time to basically create that prefix tree for every node that's in there. So it's going to be m plus something, right? Because then we also have some time complexity in our depth first search, and this is big O notation, right? So let me make sure that's clear. So it's going to be big O of m plus, and then for our depth first search, we're going to have to basically, so if there were, we can say m for number of characters in our prefix tree, and we can say n for the number of characters in the board, right? Because we're going to have to seed the depth first search n times, and then each depth first search is going to be, it's going to be 4 times, so this is like another parentheses here, 4 raised to the k, where k is like the longest string in our prefix tree that we're searching for. So that's going to be the time complexity. So m is for creating the prefix tree, and then n for depth first search seeds, and then each one of those depth first search takes 4 to the k, because there's 4 different ways you can go, and then the word can, you'll have to make 4 decisions up to k times, if k was like the longest string. And then for the space complexity, we can, if we're using these same variables, where, we said m was the number of characters in the prefix tree, well, there's obviously that space to consider, right? How the number of characters in the prefix tree, and then also you have to consider the recursive call stack for a depth first search, right? So in the worst case, that could be n, if you have like a very long string that's zigzagging all around, and it's like very unoptimally placed in the board, you might have to, in the worst case, do up to n, have n recursive calls, where n is the number of characters in the board, right? So that's for the space complexity. So let's get into the code for this problem. So the first thing we'll do is we need to make that prefix tree. So we can just make a struct for the try nodes first. So we'll call it struct try node. We'll have an array of, we're only dealing with lowercase letters here, so we can just have 26 try node pointers. And then we also need an indicator to know if we're at the end of a word, so bool is word. And then let's just make that constructor. So try node, it won't take any parameters, but we just need to initialize these variables. So first we'll set all these pointers to null. So we'll do c equals null pointer, and then is word needs to be false by default. All right, so that's our try node struct. We also need a separate class for the try itself. So let's create another class. And then it's going to have some private and public data and methods. So one private data member is going to be the root, of course, the root of the tree. So we can make a try node called root, and then initialize that in the constructor. So we'll have a parameterless constructor. We just need to set that root to a new try node. Okay, We're also going to need a destructor, right? Because anytime we use this new keyword, we've got to free that memory to prevent a memory leak, right? So let's make the destructor, and we'll do this recursively. So we'll have a custom method called clear, and we'll seed that recursion on root. It is going to be a recursive method, so it won't return anything. So void clear trinode. It's just going to have one parameter, a trinode pointer, and we're just going to loop through all of trinode's children, and we're just going to say if that children or if that child has memory allocated to that pointer, well, we need to call clear recursively on it. And then at the end of that, we can actually free the memory for the node. So delete tree node. So that'll handle memory management for, and let's see, we needed that there. So that'll handle memory management for our prefix tree. So we also want we're going to want a function to add words to the prefix tree, right? Because that's really the first thing we need to do before we can do anything. So it'll be a void method. I'll just call it add word, and then it's going to take just a string for that word that's being inserted, and that can be a copy. It's fine. So we need a trinode pointer. That way we can move down the prefix tree. So I'll just create one and set that to root at first. Then we can just iterate with the for loop through all the characters in the string s. So for auto c in s, and I put int here, it should be 4. So for auto, for each character in s, we just need to check if the trinode, if the child for that character exists, if it's already had memory allocated to it. So if it doesn't have memory allocated to it already, then we need to do so. So we'll just say trinode children. So the child corresponding to that same letter, it just needs a new trinode. And then we need to set that trinode to its child to keep moving down the tree. And then also, finally, just the last thing we need to do is indicate that this is the end of the word for the final trinode for the word that was inserted. So trinode is word is going to be true for that final final node for the final character in the word. So that's going to be true. And then, so now we can, let's make a class instantiation. Let's make an object for the tree. And I just realized this should just be try. That's what I meant there. So yeah, and everything else seems correct. So let's go ahead and make the try and then just populate it. So we need to loop through the words vector that they give us, right? So for auto, and we'll just say word w in words, we need to say my try and then call the add words method we just wrote. So, or add word method on w. So that'll basically just add each of those words to the try. And at this point, our prefix tree should be good to go. So we can start with our depth first search. So to do the depth first search, we need to seed it from every single character or every single cell on the board, right? So just to make sure we check everything. So we're just going to do this outer for loop. We can use board.size for the I coordinate. And then we need just a nested for loop. And then we're going to use j equals 0. And then j is less than board dot. And we want to do board 0 dot size just to get the size of that particular row that we're on. So for the j coordinate. Plus, okay, and then we just need to seed our recursion, and we don't have this DFS function written yet, so I'm not gonna bother putting those values in. We also need, so one more thing we need, we're gonna need a couple things actually, now that I think about it. So we need a vector of strings for our result. So that's one important thing that we need. And then at the end of this, we just return that result. The other thing that we need is actually the value for, we need to be able to access the root node of the try. So say try node star root equals, and then we don't have any way to get that yet. So let's write a public method, a getter for the root. So we'll just write it's gonna have to return a try node pointer, right? And we'll just call it get root, and it won't take any parameters, and then we're just going to return root. So that should take care of that. So now we can call my try get root just to get that root node for our depth first search. So that should be good. So now we can write our depth first search method. I'm just going to do that as a private method. It's just habit at this point. If it's not something the user of this class should have access to. But yeah, anyways, this could be public too. It doesn't really matter for this in the context of LeetCode. But anyways, yeah, so this will be a void method. It's going to take several parameters, so it needs to accept this board, right? So that's a big one. It also needs to take a result vector, right? So that's just a vector of strings, and these are both going to be, obviously by reference. And I hate, I prefer having my that ampersand or whatever it's called right before the variable, so bear with me. So int I, so we need the coordinates too. Those are not going to be global or by reference because those are specific to each recursive call, specific to that scope. So so we have board res ij. We also need a trinode, right? So trinode star tn. It's not necessarily the root, it's just, wherever you are in that prefix tree for the depth first search, and you'll see more what I mean when I actually write the method. So board res ij trinode, this should be good. I have a feeling we might need maybe one or two more things, but let's just get into this. I think this is all I can think of, honestly, for now. So, so the first thing we want to check is, we actually want to get the character rat in the board. So let's have a char C, and then we'll set that to board ij, and then that'll make our lives a little bit easier, because now we can just say, okay, so we don't want to go back and check tiles we already have in our depth first search. So an important concept here is that we've got to have a way to basically indicate we've already visited a certain cell. And so we can do that very efficiently in place and then just reset the board back to how it was at the end of this DFS call. So, but in the meantime, we're going to set, we need to ask if C is equal to hash, because that means we've already visited this tile. So we need to just return from our DFS Okay, so now let's handle the case where the character is not in the prefix tree, because if it's not, then we know we're not looking for this character at all, so we're done searching. So we can we need to, let's see, we'll have our try node. We need to actually just move that down. So it's gonna be equal to the children for character C, right? So and then minus a to normalize that to a 0 to 25 integer index. So we're gonna just move that down, and then we're gonna check, okay, if the try node for that character doesn't exist, then we can just return. Okay, otherwise, what do we want to do? Well, we're gonna want to depth first search, but first we want to check if we're at the end of a word. So we're gonna do a check. We're gonna say if try node, if this try node is word, and the other thing I forgot to do is we need to have a string word. That's what I'm forgetting. So as we do our depth first search, we're actually building the string, right, that we're looking for. At least that's the way I'm implementing this. So so we need to take our string s that's specific to the scope of this DFS call, and say, we're going to say s plus equals, and let me call that word, because there's a lot of variables here, and it can get honestly kind of confusing. So let's be as clear as possible here. So so we're going to use word, and then we're going to add that character to it, because we know, we haven't visited the cell yet. It is in the try, so this does obey the rules so far, and we can add this character to the current word we're searching for. Now, if it is a word, like if we've reached the end of the prefix tree, and the leaf node here is telling us it's a word, then we can add that to our result vector, right? So we're going to say res.push back word. And then we also want to indicate that that's no longer a word we're looking for in the prefix tree. So we can say tn is word, just set that to false. Okay, so now we can do continue our depth first search. So let's set the board at ij to one of those hashes, just to indicate that we've already visited this for the next DFS calls. And we need to make sure we're in bounds for each of these calls. So the way we're going to do that is we're going to check before we actually make the call. Like alternatively, you could check up here if you're out of bounds and then return, but I'm just going to do it before we even bother making the call. So we're going to check, okay, so if I plus 1 is less than, it has to be less than board dot size. Right, yeah, it has to be less than board dot size for this to be a valid, to be able to increase I without going out of bounds, basically. So so then we just call DFS, and let's see, the parameters are going to be, we have the board, the result array, I plus 1, j, the try node, and then the word that we're building. So quite a few parameters there. So that's it for incrementing I. Now let's subtract I. So minus 1 has to be greater than or equal to 0. And then we can subtract 1. And then we've got to do something very similar for j, right? That's just checking this is a little different, right? We have to check the size of that row, not the size of the column for j. make sure that's less than board 0.size. Okay, so now we can increment j, and then same thing for decrementing j. So it has to be greater than or equal to 0. And then we can subtract 1 from j in the DFS call. So at this point, we can literally just set the board at ij back to C, and then we're done with our depth first search. So we just have to seed it here, and this should be all of the code. So to see that, we need the board, the result. I and j will literally just be whatever those values are in our nested for loop. And then we need the try node, so we're always going to start from the root of the prefix tree and seeding our recursion. And then our word is always going to be an empty string to begin with. So this should be all the code. Let's see how we did here. So it looks good. Hopefully this video helped you understand this problem better. If it did, leave a like and subscribe. I'll see you guys in the next video. Peace.